Bismillahirrahmanirrahim. And yes, students, we are here with the part B of lecture number 8. So let's continue the discussion where we left in the last part. So we were discussing about the horizontal microcode and its timings. So each microcode instruction takes one cycle time, and functional units may require more than one cycle to complete an operation. Programmer must accommodate hardware timing or errors can result. To wait for functional units, insert microcode instructions that continue the operation. Okay, so for this last point, let me show you that. Look, this is the last one instruction in the ALU 111. It is saying continue previous operation. Okay, so this is the same thing which is written over here like this. So actually the second and third instruction which is written here, it means that as we have already discussed it, different instructions take different time. So it's not necessary that they will complete in one clock cycle. So they can take more time, and stall can occur due to this, and programming errors can also occur due to this. So programmer must accommodate the hardware time. He must know the capabilities of his hardware, that what is the clock rate and which processor it is having, and what is its limits to program the realistic and more smooth codes. Okay, and to wait for functional unit, insert microcode instruction that continue the operation. For example, if we will bombard the microprocessor that do this, do that, and it is busy in the last preceding commands. So it's not a good situation to cater for this. We have to accommodate or to give the microprocessor its due course of time. We have a special combination in the ALU with 111, which tells the ALU that whatever you were doing in the previous clock cycle, continue doing the same thing in the coming cycle or in the current cycle. So this is the same thing. Okay, and here is the example of continuing an operation. Here look at carefully that ALU has the value of 111, which I showed you few minutes back. That ALU in the ALU 3 bits, if the combination of 111 comes, it means that continue previous operation. So it is very important that whenever there is some heavy program is being done, or some such opcode is to be executed on some operands which may require more than one clock cycles. So we must give the proper time to microprocessor, different elements to continue their work, and we should not expect them to complete the task in a single clock cycle, because of course there is no magic within the computer. It has to calculate all the steps and with accuracy and with its due course of time. So it requires some time. So we have designed this 111 code in the ALU to instruct it to continue previous operation. Okay, and then when this condition occurs 111, so look here that there is no data is coming in any of the registers and from anywhere. So assume ALU operation 111 acts as a delay to continue the previous operation. So in this data, or in this slide, you can see that all the other things, they are zero. There is nothing. So you can also say that this is such a condition that if the delay comes in the last instruction of the program, that nothing to do after that. So everything, all these counters, OP1, OP2, result 1, result 2, and register interface, everything would be at 0. But if this does come within the processing, or in the middle of the processing, then we can exploit, or we can use the parallel operation, and can simultaneously fetch the operands for the next instructions, because to save our time. So let's see in the next example. Yes, here is the example. Okay, look here that ALU has 111. It means that continue previous operation, and OP1 has again a value of 1. It means that it should load the value from the data transfer mechanism. That and OP2 doesn't have any. It has a 0 value within it, so it means that we are instructing operands 2 that do nothing. We are instructing operand 1 to fetch whatever data is available at the data transfer mechanism. We are asking it to copy that data into OP1 register for further processing in the coming cycles. Okay, and then result 1 and result 2 both are 0, because no result has yet been computed. So that is why nothing to copy from there. That is why we have put a 0 in their fields. And in the register interface, look that we have 0, 1. 0, 1 means that we need to take some data from the data transfer, from the register accesses. Okay, we need to copy something from there and then put it on the data transfer mechanism. So 0, 1, and after that is 0, 1, 1, 1. So it means that this is, we are asking the register interface to put the contents of register number 7. Okay, register number 7 starting from 0. We are asking him to put the contents of register number 7 on data transfer mechanism, and simultaneously we are asking operand 1 to fetch this information and treat it as its operand 1, and similarly simultaneously we are asking the arithmetic and logic unit to continue the previous operation. So all the bits which are 1 after ALU bits, this is the preparation for the next command. Okay, they are nothing to do with the current command, because to ALU we have already instructed that continue whatever you was doing in the preceding cycle, and on the same clock cycle we are asking different elements, different organs of the microprocessor to do their works, and that few elements will be pushing the data, and few registers would be copying the data for and copy that data as operand. So this slide is illustrated and explained with the star sign. A single microcode instruction can continue the ALU operation and also load the value from register 7 into operand unit 1. This we have already discussed, that what will happen in this case. So horizontal microcode and the parallel execution. So this is the way the strings of 0 and 1 come, and every element judges the string, and it analyzes the string and decides that whether there is some instruction for that element to do something, or there is no operation instruction for them. So in this way, the horizontal microcode works and continue its operation. Okay, the horizontal microcode and parallel execution. This is the next article, the horizontal microcode and parallel execution. Because an instruction contains separate fields that each correspond to one hardware unit, horizontal microcode makes it easy to specify simultaneous parallel operation of multiple hardware units. This we have already explained in the last slide. So that we are using the instructions or the strings of zeros and ones in sequence, which is carrying the instructions for different hardware elements to do something or to continue the previous operation or do nothing, load nothing. So all this is to execute or to get benefit of the parallel operation. Okay, the next article is the intelligent microcontroller. Intelligent micro, what it does is it schedules instructions by assigning work to functional units, and it handles operations in parallel, performs branch prediction by beginning to execute both parts of a branch, and constrains results so instructions have sequential semantic, keeps results separate, decides which path to use when branch direction finally known. Okay, what is the crux of this intelligent microcontroller? Look, that in the start, when in 1970s the computer was invented, and people were very happy that it is a big giant and a big leap in the mankind history that we have achieved such a machine which can process the data as well as the numeric data as well as the alphabetical data. And no doubt it was a big achievement at that time. But with the passage of time, its capability was limited, its speed was very slow, and the central processing unit used to be working as a single point of failure and a single controlling part. But with the passage of time, when we experience that what shortcomings of the what imperfections and slowness in this computer is happening, and how can we overcome all of this? So with the passage of time, we move towards the distributed system, and every input-output device or like DVD, CD, USB, everything had its own processor which used to be controlling its mechanism, and it used to be working under the main microprocessor. So this design was adopted. Okay, but after that, with the passage of time, the capabilities and the speed and accuracy of the underlying hardware, it kept on increasing day by day, year by year. So after few time, the vertical microcode in the starting days, the vertical microcode was pretty okay with the old microprocessors and central processing units, because their speed was slow and they could not work simultaneously, and they could handle one command at a time only. So vertical microcode was pretty well for them. But with the passage of time, when the hardware capability started increasing, and we started moving towards the distributed structure, so at one moment of time, it was felt that now the bottleneck is coming from the vertical microcode, because it cannot exploit the parallelism. It cannot fully milk the potential of the underlying hardware. So the researchers they started giving importance, and they started working on the alternative ways to the vertical microcode, and the horizontal microcode was the result of all this. And in the horizontal microcode, because underlying hardware has become so much sophisticated that it can handle multiple and simultaneous instructions. So vertical microcode does the same, and it also speeds up the work with engaging the different organs of the computer simultaneously. Okay, and whenever some decision point comes in the processing, before the intelligent microcontrollers, it used to be stall used to be actually just over there, because until the decision box doesn't calculate the result of the of some operation, and then it can compare it with the set value. Until then it was impossible to decide that which branch to take. Okay, for example, if then else statements. For example, I say that at some moment of time, if the value is greater than 25, then take the A path or A subroutine, and if the value is greater than or less than 25, then take the B subroutine. So at that point of time, the program needed to calculate the actual value coming with the set value of 25, that either my computed result is equal to 25 or the greater than or less than, what is it, and then it could jump towards the appropriate subroutine. Okay, but with the advancement of the computers, what does intelligent microcontrollers, they start the processing of the both branches, and meanwhile they wait for the result to come and to analyze it with the set value, and whatever branch wins, it keeps on doing its work in the sequence, and the other branch which we had simultaneously rolled out during the processing, but it did not win the case, or it did not it was not on the decision of the if then else statement, it was not to be executed, so the computer will roll back it. So this is the whole concept of intelligent microcontroller, and it keeps the results separate and decides which path to use when branch direction finally known. Okay, and let's move forward. After the intelligent microcontroller, the important concept of branch prediction. Yes, so the same thing what I have explained in the last slide. All that concept is written here in another words with the caption of the branch prediction. A CPU that offers parallel instruction execution can handle conditional branches by pre-computing values on both branches and choosing which values to use at a later time when the computation of the branch condition completes. So you can say that the program execution is and its computation is slow, but the underlying hardware is so smart that we can do this thing. We can predict the branch, and means that we will be parallelly executing the both paths, and meanwhile when the computation of the branch condition completes, then whichever branch will win the match, that will continue, and the other branch which will lose, it will be rolled back. So this is the whole concept of the branch prediction. Okay. Coming to the next article, this is the Camming parallel execution units. Parallel hardware units, wild. and CPU must preserve sequential execution semantic as expected by programmer, and mechanisms used are the scoreboards, reorder buffer, and note when results computed from two paths, CPU eventually discards results that are not needed. Okay, so what is the timing parallel execution units? It means that, for example, if we have a conditional and unconditional code within the program, so what it will do, what the computer will do, the compiler, during the compilation of the program, the compiler will tell us that how many lines are dependent to each other, means how many commands are such commands in this program which are dependent on some previous results. Okay, got my point? For example, I have a 100 lines program, and the line number 6 is computing a result whose name is X, and this result X is being used in the command number 13 as an operand. Okay, and command number 9 is computing a result whose name we have chosen its name as P, and this P is being used as an operand in command number 67. So such dependencies, such code is called dependent code. Such code is called dependent code, and such dependencies the compiler points out it, and there is a scoreboard that our hardware are so smart that our processor is so smart that it divides both the program into two parallel execution programs. Means it filters out all the dependent instructions and always ensure that they are executed in sequence, because, for example, if as I told you that if 8th instruction result is being used in the instruction number 13 as an operand, so it is not possible to execute the instruction number 13 first and instruction number 8 after that, because which value it will assume if command 8 will not execute and it will not produce a result. So the instruction 13 cannot decide that which value to use. So this is the crux of all this parallel execution units, that it examines the code and it divides the code into two groups. One is dependent instructions and the other one are independent instructions, or their order is not important because they are not being used in any preceding command. So what the processor does, that it reorders the code, and it computes the code and generates the results, and then again on the parallel side, the dependent code and the independent code, they both are run simultaneously on the computer. And when the results are computed, once the results are computed from both sections or from the both sets, the results are again sent back to the processor, and they are arranged in the form numbering in the ascending or descending order, like and when it is displayed, the end user he cannot judge that the execution was done out of order, or which execution was done in order, because the results appears before him as in order. Okay, so you got, I think you are now I think you have understood all this concept, but if not, read it from the book again, and whenever our next interactive session will be conducted. You can ask it and I will explain you over there again. So, coming to the final touches of this chapter, we have reached up here on the summary that the CPU offers modes of execution that determine protection and privilege. This we had discussed in the start of the computer. To recap it, that we need the protection. We need the protection for this. What we do, we deploy the passwords. We deploy the firewalls in the network. We deploy the firewalls, and we ensure some specific places reserved in the memory for the program. So all of this are the protection, and which application program has what kind of rights, and which one doesn't have the rights. This comes under the privilege, and we deploy the privileges with the username, passwords, and by making their different groups like administrators, power users, normal users, and the guests, etc., etc. So everyone will have the different privileges. And the second point, the complex CPU usually implemented with microcode. Yes, because what is the importance of microcode? That it doesn't require the hardware logic, means it doesn't require the rebuilding of the underlying hardware. And that is why we can reprogram our hardware with the help of microcode, and there are two sets or the two variations of the microcode. One is called the vertical microcode. It uses conventional instruction set, and the new one is the horizontal microcode, which uses unconventional instructions. And we have discussed in the fair detail that how does this work. And each horizontal microcode instruction controls underlying hardware units. Means we had discussed it with the strings, because in our case our string was 13-bit long, but in the actual computers this might be much more complex and much more longer than this. For example, if we had assumed that our ALU can handle 8 operations, but let's say that if I say that my ALU can handle 32 operations, so it will be having 8 doubles it 32. So it will be having 5-bit ALU signals to tell the ALU that what to do with the operands. Okay, so each horizontal microcode instruction controls underlying hardware units. And if we will be having more than 2 operands, then obviously we will have operand 1, 2, 3, 4, 5, 6. So the length of the instruction will again increase, and we will have, if we will having the result registers more than 2, then the length will further increase. And here in our case, for the sake of simplicity, we said that we have a register access which has only 16 registers, but in the actual computer there are billions of registers. So you can imagine that what would be the length of the register access. The codes will remain same, that 0, 1 or 1, 0 in the most significant place, but the length of the instruction, the length of the register in the memory, that might take maybe 16 bits or 17 bits or 18 bits. So it depends upon the underlying memory, that what kind of memory or how much density of that memory is there. So in this way, the actual commands will be much more complex than our simpler example. The horizontal microcode offers parallelism, and it offers parallelism and most complex CPUs have mechanisms to schedule instructions on parallel execution units. This we have also discussed. Scoreboards and reorder buffer used to maintain sequential semantics. So up till here, our chapter number 7 is complete, and let's meet in the next class with the next chapter. And thank you for listening, and thank you for watching. And let's meet in the next class. Assalamu alaikum.